what is a micro operation? A micro operation is defined as an elementary operation performed on the information stored in one or more registers. So it is a basic and elementary level operation that goes on performs some operation on registers, right? So when we go to this level, to the register level of operation, we call it a micro operation, right? Micro operations are categorized into four types. So first is register transfer micro operations. So those micro operations which represent the transfer of contents of one register to another, fine, maybe from R1 register to R2, from some data register to some other accumulator register, like this. So this is register transfer operations. We already studied them. We saw how to represent these operations also. And the second category is arithmetic micro operations, then logic, and then shift. Let us study them one by one. So the first category is of arithmetic micro operations. So we all know what are arithmetic operations. More particularly, it is addition, subtraction. And we very well know that subtraction also is usually done using 2's complement representation, converting subtraction into addition. So these are the arithmetic operations represented here. So for example, I have to add the contents of two registers and store the answer in a third register. So this will be the symbolic representation, which means contents of R1 are added to the contents of R2 and the results are stored or transferred to R3. In the same way, this is the subtraction operation. This is the complement operation, which means one's complement, which means that every bit in R2 will be inverted, and here answer is again stored in R2. This we know, this is 2's complement, inverting each bit in R2, then adding 1 and storing the answer again in R2, it becomes 2's complement. And what is this? This is a subtraction operation, because we know R1 minus R2 is same as R1 plus R2 bar plus 1. In other words, R1 minus R2 means R1 plus 2's complement of R2. So this is also an arithmetic operation, purely an addition operation with some inverting here. So answer may be stored in R3. In this way, we can do the subtraction. There is also increment, that when we add 1 to some register contents, this will be an increment, and if we subtract 1, this will be a decrement operation. When we perform these operations, we obviously need hardware, certain hardware, where we have registers that will hold the data, and we have digital components which will do the arithmetic operations. Let us first of all see about binary adder. See the binary adder. So we know about half adder. Half adder means something as a combinational circuit which adds 2 bits. There is full adder, which means a combinational circuit which adds 3 bits. But in practicality, we see that a number consists of a number of bits like this. So if I represent, for example, a number here 7, so 7 at least needs 3 bits to represent like this, fine. And then there is another number here. Then if we add them, so we have to add first these, then we have to add these, then we have to add these in a serial way. So a circuit which performs such operation is called a binary adder. So we say a digital circuit that performs arithmetic sum of two binary numbers of any length. Fine. When we talk of half adder or full adder, at that time the number is only one bit long. But here we have any length number. So this is the actual thing which we require inside a CPU, a binary adder. So for understanding this circuit, let us take an example. Let us say we have a 4-bit binary adder. That means in which both the numbers that are to be added are of length 4-bit, are represented in terms of 4 bits. Let us say I have a number 7, which obviously will be represented by 0, 111 in 4 bits, and I have another number 3, which will be this thing. Fine, 0, 0, 1, 1 is 3. When I do the addition of this, obviously 7 plus 3 should be 10. But when at binary level I do this, it will be like this. 1 and 1 will be added. So 1 and 1 is 1, 0. 0 is here, 1 goes to carry. So 1, 1, 1 is 1, 1. 1 is here, 1 goes here. 1, 1, 0 is 1, 0. 0 goes here, 1 goes here. 1, 0, 0 is 1 with a carry 1. Fine. 1, 0, sorry, 1, 0, 0 means 1 with no carry, so the carry is 0. So the answer will be 1, 0, 1, 0, which obviously means 10. If we look keenly at this operation, what is happening? First, we are adding 1 and 1. So we are adding 2 bits. This obviously needs a half adder. 1 and 1 gives us 0 and 1. So 1 carry. So this 1, 1 and 1 needs to be added, which obviously will need a full adder. Then again there may be carry. So 3 bits means full adder. Then again there may be a carry. 3 bits, adding 3 bits means full adder. So to do this whole operation, we need here half adder, here full adder, and full adder. But in practicality, we do not use a half adder, we directly put a full adder at the first place also. So when we combine this 4 full adders, it becomes a 4-bit binary adder. So if you look at this diagram, this is a very simple one. We just put 4 full adders. FA means full adder. So we are putting 1, 2, 3, and 4 full adders in a line, connecting them, and we are done. We have created a 4-bit binary adder. And at the start, since there are only 2 bits that need to be added, the third is nothing. So we put the third bit as 0 here. So that is why the first full adder carry input of the first full adder is 0. We directly put A0 and B0 here. So this is A, this is B. So this will be A0, A1, A2, A3, B0, B1, B2, B3. So we have to add A0 and B0. Fine. So we are adding A0 and B0 using a full adder. Since full adder requires 3 inputs, the third we put as 0. Then we will get the sum and we will get the carry, because we know full adder gives us 2 things, sum and carry. Then in the next full adder, we are adding A1 and B1 and the previous carry. So that is what we are doing, A1, B1 and the previous carry. So this will be a sum and a carry. And the next it will be carry A2, B2, done. Then in the next it will be carry A3, B3, done. And if there is an extra carry, an overflow, that will go to here, C4, this thing. So this becomes a full adder, and here whatever is here, that is the answer, our answer. So we can easily, very easily create a binary adder using full adders. If I want to create a 4-bit binary adder, put 4 full adders in a line, in a sequence. If I want to create an 8-bit full binary adder, put 8 full adders in a sequence and you are done. Let us now have a look at a binary subtractor. So we know very well that a subtraction operation can be easily converted to an addition operation by this thing. If I have to do a minus b, I just write this is same as a plus 2's complement of b. 2's complement of b means 1's complement of b plus 1. Fine. So for an example, let us take the same example that I have 7 and I have 3. So 7 in 4 bits and 3 in 4 bits. And if I want to do the subtraction, I will convert this to 1's complement and add 1. So this subtraction will be converted to this thing, and when we perform the operation we get certain result here. So we know that 7 minus 3 is 4. If we look here, the 4 bits, this answer 4 bits, this is 4. Now since we have converted the subtraction into addition, that means the circuit of subtraction again becomes the same circuit of addition. So if I have to create a 4-bit binary subtractor, I will use the same circuit, the 4-bit binary adder circuit. So I will put again 4 adders in the same line. Right? Okay. Now what should be the input of these adders? It should be A. So here it is A0, A1, A2, A3. Fine. Plus 1's complement of B. B should be there, but with a 1's complement, that is inverted. So it will be B0 dash, B1 dash, B2 dash, and B3 dash. Good. And plus there should be a 1 also. So that can easily be inserted from here. So put the first carry as 1. C not the first carry as 1. And we are done. We have put A. We have put 1's complement of B, and we have also put 1 here, and we are doing addition operation, this plus by these things. So the whole subtraction is converted into an addition operation, and this simple circuit will do the needful. The answer here will be subtraction, it will not be addition. And you can also make an elaborative diagram. Instead of writing B naught dash here, you can write B naught then a NOT gate here. Right? So this way we can use the same 4 full adders to perform the subtraction of 2 numbers. And in a CPU, obviously we will not use we will not use separate 4 full adders for addition and separate circuit for subtraction. We will do some logical thing and convert it into a adder subtractor. We will use a single circuit that will do addition as well as subtraction to minimize the hardware. So for that we create a binary adder subtractor, a circuit which is doing both things. So this is we already saw that in the both adder and subtractor, this thing is the same, 4 full adders, right? And a carry is here. Every full adder has 2 inputs from here and carries, right? And there are these outputs, so this is the same. Now the only thing is that we have to differentiate between adder and subtractor. For adder this is 0 and for subtractor this is 1. So we are calling this line as M. Very simple. If M is 0, so this is for addition, and if M is 1, this is for subtraction. Good. Now another issue is that for addition this remains A0, A1, A2, A3. For subtraction it remains the same, but for addition this is B0, B1, B2, B3, but for subtraction this is B0 naught, this is B1 naught, this is B2 naught, and this is B3 naught. So now we have to do something that when there is addition, this will remain as B, and when this is subtraction, it becomes not. For that, we already have a gate in digital, which is called the Xor gate. For this type of thing, we have an Xor gate. So how will the Xor gate help us here? We can understand that by the truth table of Xor gate. If we look, this is the truth table of Xor gate. We have two inputs and this is the output. If we look keenly at it, whenever one of the inputs is 0, whenever one of the inputs is 0, the output is same as X. That means if Y is 0, output is same as X. If Y is 0, output is same as X. And if the Y is 1, output is equivalent to X bar. If you look keenly at this, you will grasp the concept. Whenever the output is 1, whenever the Y is 1, the output is X bar. That is, this thing is inverted. Whenever the Y is 1, the output is equivalent to X bar. That means this thing is inverted. This concept we can use here. We can say whenever this line is 0, the output of this XOR will be same as B. So if we put this as 0, this will be B0, this will be B1, and so on. If we put this as 1, this will be B0 bar, because whenever Y is 1, X gets inverted. That means whenever M is 1, right? M is 1, B0 will get inverted. It will become B0 dash. Here it will become B1 dash. So by this logic, we can easily create a common adder subtractor. Now, if we want to do addition, just put this 0. If we want to do subtraction, put this 1. Now let us see what is an incrementer, binary incrementer, and how can we create one. So a binary incrementer obviously means that it will add 1 to a binary number. For an example, let us say the binary number is of 4 bits. So let us say we are dealing with 7. So this is 7 in decimal, 01111. And incrementer means we just have to add 1 to this number. Whatever number there is, we have to add 1. This will become an incrementer. So we can just by this example, we can deduce what should be the circuit. So here we have to add 1 and 1. This becomes 0 and a 1 carry. Then this 1 and 1 needs to be added. Again 0, 1 carry. 1 and 1 needs to be added. 0, 1 carry, which is 1 and 0 becomes 1. There will be no carry here. So we can clearly see here we are adding 2 bits, which means we need half adder. At this step, we again are adding only 2 bits, because adding 0 is not a must. All other bits will always be 0. So no need to use circuit for this. So at this level, we say there may be a carry and this bit. So adding the carry and this bit needs a half adder. Here also we need a half adder, and here also we will need a half adder. Fine. So we obviously will need a 4 half adders for doing increment if the number is 4 bit. So a 4 bit binary incrementer will have 4 half adders. Fine. In the first half adder, the input will be 1 and the bit. So in the first half adder, the input will be 1 and bit, A0 bit. Fine. So if this is A, this is A0, this number is A, so it will be A0. Then half adder will have 2 outputs. One will be the sum, second will be the carry, which will go to the next half adder as input. Fine. Same as here, the carry will go to the next, and this will continue up to 4 stages. Finally, we will get a increment a sum of these bits. These bits will get a sum of these bits. That will be the final increment answer. Answer will be from S3 to S0. So this is a very simple logic by which we can create a binary incrementer. Now let us say I have to create a binary decrementer. So again, we know that what is a decrementer? It is subtracting 1. But we know this, what is easier, that instead of subtracting, we convert the subtraction into addition. So for example, if I have number, this binary number, and I have to subtract 1 from this. This is 7 in decimal, this is 1. We can convert this into addition by writing this is same as 7 at its place, and this will be converted to 2's complement of this plus, right? So 2's complement of this becomes 4 times 1. Right? So this operation is same as this operation. Now let us see how to implement this. So this is easy. If I have to add 1 to each bit, right? So at second, third, and fourth position, there may also be carry. So it obviously means we need full adders, right? At the first position, half adder can also work, but at other positions, we need full adders because there might be a carry at every second and third and fourth position. So that means this decrementer can be made using full adders. Since we are taking 4-bit number, so we will take 4 full adders. What is to be done in a decrement operation? Decrementer. The decrementer will just add 1, 1, 1, 1 to each bit of the number. So A0 to A0 we will add 1, to A1 we will add 1, to A2 we will add 1, and to A3 we will add 1. So 1 will be added to each digit, and there will be no previous carry obviously, and easily we will get an answer. That answer will be our decremented answer. This will be here, S3 to S0 will be the decremented answer. So seemingly it looks like an incrementer, but obviously this is not an incrementer because of this logic, 2's complement logic. It is actually a decrementer. And now we saw how to create a binary adder, then we saw how to create a binary subtractor, then we saw how to create a binary incrementer, then how to create a binary decrementer. Won't it be very nice if we had a common circuit which will do all the operations by certain and we will control those that circuit using certain control signals. So the control unit will produce certain signals. Based on that, it will be selected which operation we want to perform. And if we make such a circuit, it will be very advantageous because the hardware will be minimized. You don't have to create a separate hardware for adder, separate for incrementer, separate for subtractor. No, just a single hardware with some adjustments, and then the control unit will decide what we have to do right now. So this is the circuit which typically we may call as the arithmetic unit of the CPU. So we say the CPU has ALU. The A part, we may say that this is the A part, basic computer, A part of arithmetic part of a basic computer. What are we doing here? We are just using 4 full adders and 4 multiplexers. Right? We have 4 full adders, 1, 2, 3, and 4, and then we have 4 multiplexers here. And then we are connecting the wires in such a way, the bus in such a way that all the arithmetic operations are being done. So you can see it here. All these arithmetic operations can be done by just this single circuit. And what is going on here? We say we have two numbers, A and B. So this is A0 going here, then A1 going here, A2 going here, and A3 going here, right? And we always have an initial carry that is going here, fine. These are outputs, first, second, third bit, fourth bit, and a final carry output. And we say that this second input of each full adder is decided by a multiplexer, and the output of the multiplexer is controlled by the control lines, right? These are selection lines of the multiplexer. So everything, which operation among these you have to perform depends on these lines, these control lines, and also the carry line. So what is going on here? This is 4-into-1 multiplexer, because we are making a 4-bit arithmetic circuit. So 4-into-1 means it has one output and it will have 4 inputs. The first input will be the first bit of second number, the B0. Second will be B0 dash. Third is 0 and fourth is 1. So you can see here this line, this is 0 and this is 0 invert this line, which means 1. And the same thing is repeated for each multiplexer. So this first will be B1, this is B1 dash 0 1, B2 B2 dash 0 1, B3 dash 0 1, right? So since because of this type of wiring here, it seems a little difficult to understand what is going on. So I have converted this circuit to this simpler one for sake of understanding. So whatever is this wiring putting here as an input, I have directly wrote that here. So this is the same circuit on the right hand side, this thing, and this is the same multiplexer which was here. So because of this, all this, what is going here, B0 will go to first position, B0 dash to second, then 1 and 0, then B1 dash 1 and 0, B2 dash, sorry, 0 and 1, B3 dash 0 and 1, fine. And since this multiplexer has to choose between 4 options, so it can only put output, its output will always be one of the 4 options. So when you have to distinguish between 4 options, you need 2 selection lines. That means every multiplexer will have 2 selection lines, S1, S0, S1, S0, S1, S0, right? So this is very simple. So if this S1, S0 is 0 0, the first line will be the output, means B0 will be the output here. And if this is 0 1, B0 dash will be the output here. If this is 1 0, the third output will be here, that is 0 will be here. And this, if this is 1 1, the fourth output, that is this one, will go here. And same things will apply on each multiplexer. So for example, if this is 0 0, B2 will be here. If this is 0 1, B2 dash will be here. If this is 1 0, third, that is 0 will be here. And if this is 1 1, 1 will be here. Okay, now let us create a function table so that to understand what will be the various combinations and how will it work. So this is a function table of this whole circuit. So let us say, so there are control lines are S1 and S0. This is S1 and S0, fine. Selection lines. And we also have a C in here, the carry thing. Okay, let us take the first thing. If this is 0 0, so S1 and S0 is 0 0, So if this is 0, 0, what will be here? B0, B1, B2, B3. So A0 will be added to B0, A1 will be added to B1, A2 to B2, A3 to B3, like that. So this is a simple addition then going on. So what will be Y? It will be B actually, Y. So Y will be B. And if there is no carry, so it will become an addition of circuit. So this whole circuit will get converted to a simple binary adder. So the output will be A plus B. So just by putting this carry as 0 and putting S1 and S0 as 0, 0, this whole thing will become a binary adder. Now if we keep this thing as 0, 0 but change this carry to 1, we keep it as 0, 0 but change the carry to 1, it will obviously be A plus B plus 1. So this we call as addition with carry, and there may be a carry from previous addition that we are adding. Now the second combination will be 0, 1 of these two, the second combination 0, 1. So if this is 0, 1, this will be B not dash, right? The second thing. So this is B not dash. Here B1 dash, B2 dash, B3 dash. So it will become, Y will become B dash. So the answer will be A plus B dash if the carry is 0, and if the carry is 1, it will become A plus B dash plus 1. So this is A, this is B dash, and this is 1. So the adder is adding all three. So it will become A plus B dash plus 1. And we know this is the subtraction operation. And this operation we call as subtraction with borrow. And let us take next combination, which is 1, 0. So if this is 1, 0, here it will be 0, 0, 0, 0. So that means 0 will be added to A. And if the carry is also 0, that means nothing will be added to A. Right? A plus 0 plus 0, which means A. So this whole circuit will be like a buffer. So it will transfer A. A will be transferred from here to here. Right? And if in the same case the carry is 1, then it will become an incrementer. So if in the same case this is 0, 0, 0, 0, but from here we are inputting 1, so obviously it will become an incrementer. So we are adding just 1 to the whole A, so it will become A plus 1. So this means that if I have to convert this whole thing into an incrementer, just put S1 equal to 1, S0 equal to 0, and put this C in equal to 1. So this whole thing will become an incrementer. And if I want to convert this whole thing into decrementer, we just studied few minutes back that in a decrementer, this second line should be 1, 1, 1, and 1. So to put 1 here, we need to introduce 1, 1 here. So if I put 1, 1 here, this will be the output, that is 1. So this will be 1, 1, 1, and 1. So that means 4 ones will be added to the 4 bits of A and no carry. So this is, what is this? This is a decrementer. So in that case, if this is 1, 1, but the carry is 0, this will become a decrement operation. And lastly, if this is 1, 1, that means this line is 1, and we also put a 1 here, fine. So we are adding A to 1, 1, 1, 1, and also adding an extra 1 there. And if we do it on a notebook, this operation, that adding, we have a 4-bit number, we add 1, 1, 1, 1 to it, then we add an extra 1 to it. So it will be a transfer thing. A will remain unaffected, because 1 1 1 1 plus 1 will become 0 0 0 0. Fine. So it will be a transfer operation. A will remain unchanged. So this combination will result in a transfer operation. So we just saw that how we can use a single circuit to create this whole arithmetic unit of a basic computer, and this arithmetic unit is mainly doing these operations. There should be more operations in this multiplication, division also, but let us in this thing we are just considering these operations. So in total, this 1 2 3 4 5 6 and 7 operations are being performed by this thing, 7 arithmetic operations. So this is how we can use a single arithmetic circuit to do these many operations.